Okay, this is example 5. Okay, the question is determine the rate of change of the input voltage in response to the input square wave as shown for ideal integrator. Okay, this is for ideal integrator. As you can see, ideal integrator dia punya konsep is ada feedback capacitor daripada output, okay, pergi kepada input. Alright, so the output voltage is initially 0. The pulse width is 100 millisecond. Okay, so question 5b, describe the output and draw the waveform. Okay, we know that the formula for this kind of circuit, okay, amplifier circuit, the formula to find for the rate of change of the output voltage is delta V out over delta T equals to negative V in over R input times with C. Okay, so this is the formula for the case of op-amp integrator, okay, which is ideal integrator. Okay, in this question it is said to be an ideal integrator sebab for the feedback here is only capacitor. Another one is the practical integrator. Practical integrator, if we refer back to our last lecture, okay, what is the difference between ideal and practical? The difference is here, the feedback here. Okay, for ideal integrator amplifier, okay, there will be a feedback capacitor from the output to the inverting input, whereas for practical integrator, okay, there will be another here connected in parallel with this capacitor. Okay, there will be a resistor, okay, a resistor connected parallel with this capacitor, and that resistor is called as RF, the feedback resistor. Okay, that is practical integrator. Okay, now this question, it is an ideal integrator. All right, now this is the formula. Okay, so the question is asking you to find the rate of change of the output voltage. So means, what is rate of change? Rate of change is this one, delta V out over delta T. So this is the rate of change. So is equals to negative V in R input times C. So we just fill up the formula. This is equals to negative, our V in is given as here, V in positive and negative 2.5 volt. It's a square waveform input into the amplifier. Okay, so since it is a square wave and it has two positive 2.5 and a negative 2.5, so first we find out the rate of change of the output voltage during the time that the input is at positive 2.5 volt. Okay, this means that the capacitor is charging. Okay, so when the time input when the input is when input positive 2.5 volt, okay, which the capacitor is charging, delta V out over delta T is equals to negative V in 2.5 divided by Ri times C. Ri is 10 kilo ohm, okay, and a capacitor is 0.01 microfarad, right? So you will get the answer as negative 25 kilovolt per second, or this is simply 25 millivolts per microsecond. So you have to be careful for the unit conversion. Okay. Okay, now let's go and see when first. Alright. So now let's see when input negative 2.5 volt. When input is negative 2.5 volts. Okay, what happened? Okay. Substitute into the formula. Delta T of delta V out over delta T is equals to negative. So this time the input is negative. Okay, 2.5 volt divided by 10 kilo. Okay, everything is just the same except the value unit, right? So now you will manage to get the final answer as 25 positive 25 millivolt per microsecond. So be sure that you note the final unit when you answer your examination. Alright. Okay, this is 5B. The question is asking you to describe the output and draw the waveform. Okay, go back to the question. It is given that, okay, maklumat yang diberi, the output voltage is initially 0. Ada dua maklumat yang kalau kamu perasan pada soalan tadi. And then the second one is the pulse width is 100 microsecond. Okay, so these two are important information for you, okay, to answer this question. So just now we managed to get the rate of change of the output, which is delta V out over delta T. This is the rate of change. Okay, we managed to get as positive 25 millivolt. Okay, and this is for when it is 2.5 positive 2.5, and this is when the input negative 2.5. Okay, so the value is just the same except the polarity. Okay, so is the 25 millivolt, and this is negative 25 millivolts per microsecond. So this one I want you to have this unit. Okay, that's why unit is important, so don't mess out with the unit. Alright, because why is the unit is important? Okay, now because we are going that this question is asking you this time, describe the output. It's no more the rate of change of the output. Okay, this time is asking about the output. Okay, so only the output means if it is the output means it is only delta V out that you need to find out. Okay, so how? V out is delta V out is equals to 25. Remember just now we get 25 millivolt per microsecond, right? Okay, times with the pulse width, okay, is 200 microsecond. Okay, the pulse width is given as 100 microsecond. Okay, so for the complete transition from a negative 2.5 to positive 2.5, okay, it requires a double pulse. Okay, double the pulse, so we manage to get the pulse width as the resulting pulse width. Okay, because here as you can see it's a delta V out. Okay, delta V out means it's a range from here to where, from here to somewhere. Okay, okay, so it is a range, so that means the pulse as well is and the pulse the required pulse taking for transition of negative 2.5 volt and positive 2.5 volt, so means the total pulse width is 200 microsecond. Okay, good. So now you can simply cancel out. Okay, cancel out. Okay, microsecond, leaving your answer only the voltage value, right? Okay, so now you manage to get the value of delta V out is 5 volts, right? Okay, now how to draw the output waveform. Okay, for this kind of amplifier, it is integrator. It is an ideal integrator kind of amplifier. Okay, the input V in. Okay, the input is in square waveform. Okay, so the output will become a triangle waveform. Okay, okay, if you refer back to your lecture note, when the input is a positive, is at positive, okay, the output is a negative going ramp. When the input is at negative, okay, the output it is called a positive going ramp for the output. Okay, so how to draw it? We know the value is 5 volt. Okay, 5 volt is the delta V out, means it has a range. Okay, the range is from what? 0 to 5. Okay, but we have to know whether it is negative or positive. Okay, we have already the information. The output voltage is initially 0. Okay, so means at initial here is the output is 0. Okay, let's say start from here. This is V out. Okay, this is the V out. V out start from 0. Okay, so during the time the input is at 2.5 volt. Okay, bila input is at 2.5 volt, here positive 2.5 volt. Okay, the output will go from 0, the output will go from 0 volt to negative 5 volt. Okay, that's why it is called a negative going ramp. Okay, so this is how the output will look like. Okay, the output will become like this. So it's about the triangle, so I take a little bit here, start. Okay, so let's say this is 0 and this is negative 5 V out. Okay, so it will ramp down to negative 5 here. Okay, sorry, my drawing is getting a bit messy. So this actually, your solution should be somewhere around clean space here, but right. Okay, right, so see this going ramp down. Okay, and then during the time the input is at a negative, the input is negative 2.5. okay, the output will ramp up. Okay, will ramp up from negative 5 volt to 0 volt. Okay, so it ramp up. Now it's the shape of a triangular waveform. Okay, so similar at this point. Okay, at this point, okay, when it is the input is ramp up to positive 2.5. okay, step up to positive 2.5, the output, okay, is ramped down. Okay, so actually, okay, the output will ramp down back. Okay, so the waveform continues like that. So now, as you can see, it's a triangular shape of waveform. Okay, with peaks at 0, peaks at 0 and negative 5, negative 5 and 0. Alright, that's it for example 5.